Extrema is a fancy way of saying min or max. It's a general way of saying it. So a mathematical definition of the word extrema would be if I have f is defined on a close or on an interval I containing some c, then I can say that fc is the minimum value of f on I if f of c is less than or equal to all the other f of x's for all x in that interval. And then I can also say that f of c is the maximum of f on I if f of c is greater than or equal to f of x for all x in that interval. So mathematically noting that if your function value f of c is smaller than every other f of x value, then it's called a minimum, and if it's larger than every other f of x value, then it's called the maximum. This is kind of the general idea behind extrema, but there are two primary kinds of extrema. We got global extrema. Global means across the globe. It also means kind of the whole thing. So another word more mathematical is to call it an absolute max or min. And we can say that means it's the highest or the lowest in the entire function. So the opposite of that, or the other kind, would be we call a relative or a local max or min. And this is the highest and the lowest in part of the function, and it typically is a turning point. So I can have different kinds of local mins and maxes. We've got a function that looks like this. I could say that this is a local min because it's the endpoint of the graph, and in that area there's nothing, in that local area there's nothing below that. I could say that this is a local min, but this is also called the absolute min. This is a local max, but it's not an absolute max because there is no absolute max. And this graph really would have no absolute max because it increases without bound. So just getting these words down so that we can have the same language is going to be important in what's coming. So let's go to the next thing. We have a graph, this kind of graph, and we're just going to characterize some features of this graph. So we have local mins and all the places that those occur. Well, let's first describe the x values where they occur. So where they occur at really means an x value. So if I say local min occurs at x equals, well, I could say negative 12 because that would be this one. I could say negative 9, that would be this turning point. I could say negative 1, that would be this turning point. And then I could say negative 1 or positive 7. So those would be all the possible places where my local min occurs. Sorry, just fixing this here. Sorry, that's negative 7, not negative 9. Okay. The next one would be to say local maxes. Let's see where those occur. A local max occurs at x equals, and I can say negative 10. I could say negative 4. So that would be these. I could say positive 2. And that's really it. So those characterize where they occur, and these would be kind of like if they occur at, those are like x values. Now if I say what are those values, not just where do they occur, but what are the values? Remember, anytime I mention a value, that means a y value. It's kind of a shorthand for saying y value, so the value of a function is just the y value. But I know that the relative min occurs, relative mins occur at or sorry, not the relative min occurs at relative minimum values because we're talking about y values. We know where they occur at. Well, those y values are -4. At x equals 12, we got -1. We also have that same y value at x equals -1. So +1 is another one. And -1 right here would be that one. And then my relative max values happen horizontally at these places. So at -10, we've got a max value of 5. So that's a relative max. Even though it's a cusp, it's right there. We've got another relative max at 6. We've got a relative max at 3. So 3, 5, and 6. So these would be like my y's. Now there is something that we just mentioned before called an absolute max. And the absolute max we can describe it. It occurs at this point right here. The absolute max is right here. At x equals 2, the max value occurs at 6. So the value is, x equals 2, my bad. We have a value of 6. And the absolute min happens at, look at the smallest point of the graph, that's at x equals -7. And that should say max value. And then min value of -4. So coming up to this graph, if I highlight all the possible max values in one color, here's a max, here's a max, here's a max. Highlight all the possible min values, here's a min, here's a min, here's a min, here's a min. And then let's just circle the absolute max and the absolute mins. That's what we just described. Now, let's look at the derivatives at these different places, because sometimes we're given a graph, in which case it's really, really good. We can see from the graph where these things are. But sometimes we're not. So what we want to do is we're kind of trying to characterize where the absolute maxes and mins are of a function if we don't really have the graph. If I looked up here, we had different kinds of locals and mins and maxes. We had these, which were endpoints. We had this was a cusp, and then we had these turning points. And those really kind of describe the three different candidates that we're going to test. This is called a test for extrema, or a test for absolute extrema, which is also called a candidates test. It's called a candidates test because we are going to look at all the possible candidates for absolute max and absolute min. So to do the candidates, you kind of want to test all these different kinds of places. So like I said, there are three different primary kinds of places. We have all the turning points, and mathematically those are all the points where f prime equals 0. Then we want to test all the cusps, which are all the points where f prime does not exist, because there's no derivative at a cusp. So in parentheses, this is turning points. The next one are cusps. And finally, we want to check the endpoints, because we can describe a derivative at the endpoints, but they could potentially be the absolute maxes or mins, just depending on how the graph is drawn. So kind of slipping back over here, relative extrema, those are possible places where absolute extrema could be, but relative extrema, they occur at all three of those possible places. So places where f prime of x equals 0, cusps, and endpoints. Those are the three kinds that we want to test. You should be able to kind of analyze and figure out where all those are. Cusps, this is basically saying where f prime of x does not exist. And this kind of points to this idea that the derivative does not exist where you have different places. One of them are these cusps. Other places where the derivative does not exist, but you wouldn't have a max or min value, is places where the function is not defined. So we call those points of discontinuity, or holes. And we also have places where the derivative does not exist. Those are vertical tangents. And vertical tangents do have values to them. Like, I look at this graph with a vertical tangent here, and I know that f of 0 is 0. This is actually the graph of f of x is equal to x to the 1/3, or the cubed root of x. And if I take a derivative of this, I know that I get 1/3 x to the negative 2/3, which is the same as 1 over 3 times the cubed root of x squared. And I know that at x equals 0, f prime does not exist. So these last two are kind of a little bit of a distinction. You don't necessarily need to always test them as part of the candidates test to see if there's absolute maxes or absolute mins. Clearly, this type here, this letter B, where the function is not defined, that is not a candidate for a local min or local max, because there's no function there. And vertical tangents really wouldn't be, because to have a vertical tangent, your function is continuing vertically and in both directions. So this really is also not a candidate. But there are other places where the function, where the derivative doesn't exist. So just to kind of compare them with cusps, it's important to kind of see that. Now, we have this thing that we also call critical points. And critical points really are any point where f prime of x equals 0 or f prime of x does not exist. So critical points are actually points on the graph. And if I want to generalize, even though this f prime does not exist, those could be vertical tangents. It could be, it doesn't have to be, but it might be. They might also be cusps. What I really kind of want to point out is that these relative extrema occur at endpoints or critical points. If you're going to be a relative extrema, you're going to occur at one of these places. So we keep endpoints are the ones that people always forget about, and critical values are a lot easier to kind of think where that comes from than you might be thinking. So here's an example. I've got f of x is equal to x squared over x squared minus 4. If I do an f prime, we're going to do quotient rule. Sorry. So f of x is equal to, let's do low d high, so x squared minus 4 times 2x minus high d low is x squared times 2x over low x squared minus 4 squared. I've mentioned multiple times that we are going to want to become masters of factoring. So I'm going to go f prime of x equals, I'm going to pull out a 2x. And if I pull out a 2x, I get x squared minus 4 minus x squared. So that just gives me a negative 4. And then I get x squared minus 4 squared, which is the same as negative 8x over x squared minus 4 quantity squared. That's my derivative. And as far as the critical points go, that's going to happen at places like x equals 0, because that makes the numerator equal 0, and x equals plus or minus 2, because that makes the denominator equal 0. And now we can describe those. At x equals 0, f prime of x equals 0, so that is a turning point, also called a local extrema. And at x equals plus or minus 2, f prime of x does not exist. Now, if I compare that to f of x, I also know that f of x, or I can just say f of plus or minus 2, also does not exist. Given that, and given what I'm aware of with this function, and I kind of do an analysis of the original function where I know that because those are values in the denominator, that means that these are vertical asymptotes. So that's the kind of discontinuity they are. That's the kind of derivative not existing that they are. So if I mindlessly take a derivative and I get a value like this, I do want to compare that with the original graph and see what kind they are. Okay, more applications of this is something we call the first derivative test to see if a function is increasing and decreasing on an interval. So this is a very colorful graph in my view. It's not colorful on yours, sorry, but it shows all the places where in blue you have increasing slopes, in pink you have decreasing slopes, and in yellow you have horizontal slopes. So if I, given, I'm sorry, it's yellow, I might make it more like a darker color here so you can, that shows up on the video at least a little bit better. Again, not sure how YouTube's doing with high def these days, but okay. That's a little bit better. One question we commonly ask about something like this is, where is this function increasing and decreasing? So when I mean with where, I want to point out the x values. So I'm giving kind of like a domain here of increasing. Well, this graph is definitely increasing from negative infinity to this point, this turning point here, because I've got turning points here, here, and if I kind of characterize in yellow this increasing, and this is increasing. Whereas in blue, this is decreasing. So that's sort of the little check we're doing here. So let's come back to this label of increasing from negative infinity to negative 2. And when I talk about increasing, I don't want to include the negative 2. Then I'm going to go from this point, which I'm going to give you right now, since I didn't really give you that point. That is 3/4. Let's put it down here. That is 3/4 comma negative. I don't know. I don't really know, but it's 3/4 comma something. Can't remember what graph I used on this one, but that's okay. We'll just kind of make it at 3/4. So if I say that's 3/4, that is 3/4 infinity. I would have to give that to you, and that's increasing because f prime of x is greater than 0. My derivatives are positive, so it's a visual way of showing that, but that's what it means. It's decreasing on the opposite interval from negative 2 to 3/4. And that's all the places where f prime of x is less than 0. Basically, the first derivative test states if f prime of x is greater than 0, then it is increasing. And if f prime of x is less than 0, then, and I'm going to kind of erase this and get more specific, then f is increasing. And then we're going to say then f is decreasing if f prime of x is less than 0. Oh, that's the summary. I'm getting ahead of myself. We'll slide that down there and keep moving on. Okay, some examples of things that we can do with this. This is a very common direction set, and I'm going to try to show it can be very thorough with a function like this. It's a third degree polynomial, and if I want to find the critical points, I'm going to take f prime of x. So I get 3x squared minus 12x, and I'm going to set that equal to 0 because there are no x values that make it undefined. I would kind of consider that. Where is it undefined? Well, it's not going to be undefined anywhere. So I factor a 3x out, and I get x minus 4 equals 0. My critical points are at x equals 0 and x equals 4. Okay, so we go back to, it's asking where is f prime of x greater than 0, where is f prime of x less than 0. Well, I can do a sign test on this. I'm going to do a sign test by plotting 0 and 4. And I know that at 0 and 4 they are equal to 0. And I'm going to just try to figure out what the different signs are. Well, if I plug in a number greater than 4, I know I'm going to get a positive. If I plug in a number, okay, so back up, you're asking where am I plugging these in? I'm taking them and I'm plugging them into the derivative. Because I want to find out, is f prime of x greater than 0, and is f prime of x less than 0? It's a test to find on where the function is increasing and decreasing. And increasing means f prime is greater than 0, and decreasing means f prime is less than 0. So I'm plugging them into the derivative. Numbers greater than 4 are positive. This is going to alternate, positive, negative, positive. So I know right away that's increasing on negative infinity to 0, and from 4 to infinity. And it's decreasing on 0 to 4. Okay, next question asks, apply the first derivative test to identify any relative extrema. So, let's see, for any relative extrema, well, I know that my candidates are endpoints, which we don't have because this is infinite. No, we do have endpoints, my bad. This is on negative 2, 6. So, if I kind of t-chart out my possible candidates, and I'm going to call these candidates, I apply the first derivative test to test these extrema, so those are 0 and 4. This is the first derivative. So C, we look at the first derivative. If I plug in 0 to the original function, I get 15. And if I plug in 4, I get 64 minus 96 plus 15, which is equal to negative 17. And this is kind of like, part C says apply the first derivative test to identify all relative extrema. And then part D says to identify the absolute extrema. Well, part D really has to do with the candidates. I should actually slide this candidates down to part D, and we'll call this extrema. Sorry, I'm ignoring my own directions. But these extrema come from my critical points, whereas my candidates now must also include endpoints and places where it doesn't exist. So endpoints, I need to check -2, and I need to check 6, because those were my endpoints. Sorry, I'm doing too many arrows. They come from here. Those are where my candidates come from. So if I plug in -2, I get -2 to the third plus minus 6 times 2 squared, so minus 24, and then plus 15. So I get -17. And then if I plug in 6, I get 216 minus 216 plus 15, I get 15. Okay, now that I've done all that, I can identify what's the smallest number I get out of all this. Well, the smallest number I get out of all this is -17. So my absolute extrema, I could say my absolute max occurs at 2 places, 0, 15, and 6, 15. And my absolute min occurs at 2 places because they are the same thing. For -17 and -2, -17. Since they both have. If it talks about value, my max value is just 15, and my min value is -17. So let's move on to a few more. Number 2, I'm looking at taking a first derivative. F prime of x is equal to 4x cubed minus 32. If I factor a 4 out, I get x cubed minus 8, which then I could keep factoring and get x minus 2 and x squared plus 2x plus 4 because it's difference of cubes. And so my critical points are 2. Actually, it's just 2 because x squared plus 2x plus 4 will not contribute a 0 to that. So my critical point is 2, and my interval would be to plug this in, and I know it's going to be positive, negative on the derivative. So my function is increasing on 2 to infinity and decreasing on -infinity to 2. Okay. Next, I'm going to test my point. So I'm actually going to do this all in one table now. It's going to make more sense that way. So I've got x and f of x, and I'm going to test 2. I'm going to test -5, and I'm going to test +5. Those last two come because they're endpoints of the interval. Now, you guys can decide, does it make more sense to use synthetic division or just to plug it straight in? Right now, I'm just going to plug it straight in because I can. I got 2 to the 4th, 16 minus 64 plus 4, so that's 20 minus 64 and -44. 5 plugged in is going to give me 625. That's going to be plus 160 plus 4, so that is 789. And then 5 plugged in here is going to be 625 minus 160 plus 4. So that's 62 minus 16 is 46, so 469. And then finally, my absolutes. If I look at an absolute max and an absolute min, my absolute max occurs at -5, 789, and my absolute min occurs at 2, -44. So my absolute max was an endpoint, but my absolute min was a turning point. Okay, number 3. I want to get a derivative going, so f prime of x is equal to low d high minus high. Sorry, low d high is not x times 1, it's x plus 1 times 1. So x plus 1 low d high minus high d low over x plus 1 quantity squared. And that's going to be 1 over x plus 1 squared. So my critical points occur at -1, and I get this going. And I have a -1 here, and I know that it's going to be positive, positive. How that happens is basically how this graph looks. But alas, I know that if I kind of try to graph the graph off here, I've got an x-intercept of 0, 0. I have a vertical asymptote at -1, and this vertical asymptote is a double asymptote. So really what's happening, no, it's not a double asymptote, it's a single asymptote, looking at the original function. To the right of that, it's going to be increasing. It's basically going to do something like this. It's got a horizontal asymptote at 1, so it's actually going to be more like this. And it's going to look a little bit like that. So that's kind of the split that's happening on this graph, if I just want to get a visual. But anyway, back to this. I'm looking for candidates to test. And I cannot test -1 because -1 does not exist. There's also no endpoints, so there's nothing to test there. So there are no absolute maxes or mins, because this graph is just infinite in both sides. Finally, f of x is equal to sine x plus 2. If I do f prime of x is equal to cosine x, and I want to set cosine x equal to 0, and I want to figure out all those places where x is the cosine of x is equal to 0. Well, cosine of x is equal to 0 at pi over 2, 3 pi over 2, 5 pi over 2. So it's pi over 2 plus or minus pi times n. Those are all the possible places, and if I want to put that on a chart, I can go negative pi over 2, pi over 2, 3 pi over 2, etc. And if I kind of try to figure out where is cosine positive, it's positive between negative pi over 2 and pi over 2, negative, positive, positive, negative. It's going to keep going like that in both directions. This is actually, oops, I did not alternate those here correctly, minus, plus, there we go. I don't really have endpoints of an interval, but I know that if I look at this, this is a max, because the graph is going from increasing to decreasing right there at pi over 2. And this right here is a min, because the graph is going from decreasing on the left to increasing on the right at that point. So if I translate that, my maxes are all occurring at pi over 2, and it's not plus or minus pi times n, it's plus or minus 2 pi times n. And my max value that happens is the max value of cosine, which is 1. 1 plus 2 is 3. And my mins occur on the opposite ones. So I could do negative pi over 2 plus or minus 2 pi times some constant n. And that's going to be a value of 0, or sorry, negative 1 plus 2, which is 1. So these are all the there's an infinite number of maxes and mins, because sine x plus 2 literally just looks like this. Take a sine graph, shift it up a little bit, and I'm cycling between 2, sorry, draw every eta, I know, between 2 and -2. And the maxes are occurring at places that are pi over 2, then add another pi, or add another 2 pi, so pi over 2, plus 5 pi over 2, and all those, and then the mins are occurring here. And that's what this reflects. That's it.